very popular in process synchronization, and we will also see like how that problem we can overcome using semaphores. Okay, so by now semaphores we already know how many types are there, why is it being used. We will check it accordingly. Now, the problem that we are discussing today is called the dining philosopher's problem. Okay, so first let us check in this diagram and let us try to understand what is dining philosopher's problem. So let us say we have a situation like, for example, there are five philosophers. Okay, there are five philosophers. That means five set of philosophers group of people, and they are sitting in a dining table to have a bowl of rice. Okay, and now each of the philosopher has a choice, mm, to take two forks. Fork means the spoon to have the rice bowl. Okay, so let's say P0 is one of the philosopher, and it is having two choices to pick the fork from the left, or you can pick it from the right. Okay. The order we will see, like who will pick first accordingly. Then similarly, T1 is also one who can pick either of the fork, like F1 or F2. So, so, so accordingly, in that way, different can pick different. You can say fork. Okay. So that is one of how this is one of the situation you can say. Okay, but there will be problem, like for example if it's a round table kind of you can say arrangement. Okay, then let's say for example P1 and P0 is there. If they are coming in a serial order, like for example first P0 will come, he will take the fork, he will eat, then release, then P1 will come, P1 will take the fork F1 and F2. That way it's fine. But what if, let's say, we have a case, like for example, P0 is there, he has to take two forks, one to the left and one to the right. Okay. At that situation, only P1 comes. So for P0 and P1, F1 is a common fork. So who will get it? That is a challenge, isn't it? And if suppose one of them gets the fork, okay, the process or the other philosopher has to wait. So philosophers here are actually the processes. Okay. Similarly, between P1 and P2, P1 can choose the fork F1 and then F2, and P2, F2, and F3. That means F2 is a common fork between the two philosophers or the processes P1 and P2. So if it is not in a sequential way, that means it's not that one is coming little bit later or one has to wait. If suppose we have a situation that both are there at the same period of time, then who will get? And if someone gets, who will wait? Then that waiting will be how long? So that will be a kind of a you can say a problem. Okay, so that is the point where we will be using the concept of semaphores to overcome such kind of situations. Okay, so let us see. I have written, let's say, a kind of a function in C. So let's say I have a philosopher function. Okay, so the main part of the body is this one only, this part. Okay, whereas the other part will be like true for all the conditions. So I have a function philosopher. So under this, what I have written, I've written a code. Now, first of all, I have a while condition which states that it is true for all cases. Okay, like it's a kind of an ideal situation. Okay, so this will be executed. Now, let's say thinking is one function. That means it's a kind of a state where the philosopher has not taken the fork yet, but it is in the initialization stage. That means the deciding phase where it is contemplating like which fork will it be taking. Now, from here, the main thing starts. Okay, so we have to understand a little bit carefully. So first of all, it will say take fork I. Okay. So take fork I. Now what is I? That we have to know. Okay. So let us say I is nothing but the you can say the index that we will be mapping for every process. Okay. So let's say for example, how many process we have here? We have five processes. The value of first process, its suffix is zero. Okay, the minimum value and the maximum value is 4. All right. Now, let's say, for example, this statement take for fork I. So, this statement, how will it be executed for the first philosopher? In place of I have to put 0 for the first process if I'm testing for the first process. Okay. So, if this is the case, then I value will be here what? So, for the first one here, I value I is equal to 0 because for every process the I value will change. Like for first process or first philosophy I is 0, for the next one I is 1, for the next one I is 2. So according to different philosophers the value of I also will be changing. Okay, and here the suffix of p like 0, 1, 2, 3, 4 will be kept same with the value of I. Okay, so let's say for example the first case is if the philosophers are appearing in serial order. That means first P0 has come. Okay, so how will it take the decision? Like which fork will it pick? So this will he will take make the decision using these two statements. So what will happen is in this loop. So first of all, this part when it will execute, take fork I. So which part of the fork it will take? Take fork I. So if I execute this one, take let's say fork I. Okay, take fork I. So what is I here? 0. That means it will be taking which fork? Fork of 0. Okay, so what will happen is next one that we have, so he has chosen which fork? F0. Okay, only P0 is there thing as of now, others have not come because we are saying that philosophers are appearing in serial order, it will go one after another. Now let's say next we have is this code. So we are having take fork I plus 1 modulo n. Okay, so basically based on the value of this one we will be able to know which fork will it be taking. I plus 1 modulo n. Okay, but I know what is the value of I here. What is the value of I? 0. So in place of I, what will I put? 0 plus 1. So 0 plus 1 is what? 1 modulo 5. So let me write this also. Modulo 5. Okay. So what is 1 modulo 5? What this modulo gives me? Modulo always gives me remainder, isn't it? So 1, if I have to divide 1 with 5, what will be the remainder that I'll be getting? What is the remainder that I'll be getting? So 5, how much are 1? I don't have anything because 5 ones are is 5, right? So it has to be 5 zeros are 0. So 1 will come down. So 1 is the remainder. For those who don't know like how this functions, you can refer to your programming where you have operators, no arithmetic operators. So you will be knowing the difference between divide and modulo division. So again, I'm just for clarity, I'm saying that modulo division will I will divide 1 with 5, I'll get remainder how much? 1. So what will this 1 tell me? So what will this 1 tell me? This 1 will basically tell me that the first process P0 will pick fork 0 and fork 1. Okay, so for the first philosopher it will pick fork 0 and fork 1. How did it pick? Because we have executed these two codes. Okay, then what is the next code here? Eat. So using this eat function, basically the philosopher will be able to consume the rice. Okay, then once it has consumed, so what it will do, it has to release the fork. So how will it release? So same code only, fork I, that means it will release the first fork, fork 0. Okay, and another one, which one will it release? Same fork only, fork F1. Okay, this fork also. So same code is there, just as in the first one it is taking the fork, and here it is putting back the fork. Okay, so that is the thing. So it will be doing that. So it will come out of the loop. Once it comes out, again it will be checking. So this while loop will be executing until we have exhausted all the philosophers. Okay. So next is which one? It's P1. So I value will be now. What will be I value for P1? What will be the value of I? So for the next one, the value of I will be 1. Okay, so how will the code execute? So code execution is same. So here take fork I. So what is the value of I? 1. So P1, for P1 it will take fork F1 because it will run this code, and once it takes this, it will take the other fork. So how will it decide which fork? It will run this code. So what is the code here? I is 1. So 1 plus 1 is how much? 2. 2 modulo n. What is the value of n? 5, because the number of philosophers are how many? 5. So 2 modulo 5 is how much? What is the remainder? 2 again, because 5 zeros are 0. So 2 minus 0 is how much? 2. Okay, so it will give me the remainder 2. So which fork will P1 pick? For the first one, for because of this, it has picked F1, and because of the second code, it will be picking F2. Then P1 will be consuming the rice present in the bowl, and once it is done, it will put back the first fork I, that is for F1, and the second fork, that is F2. Okay, so this is first case where it's very simple when philosophers are appearing in serial order. That means it's not coming together to have the rice bowl. It's not like a dining kind. First it will come, then P0 has consumed, it has released, then after some times P1 comes. So this is very easy to execute. Okay, so this is one of the case of dining philosophers. Then we will go to the second case. So as of now, is it clear? The first case. Any doubts for the first case? You can write in the comment section. Okay. Others? Okay, very good. Okay. Okay. For the ones who had some issues with the network, so I can just say that this is a serial process of arrangement of process. Here, the philosophers are the process. The main aim is that the philosophers should be able to consume the rice bowl, which is present at the center of the dining hall. Okay. Now, this is the seating arrangement of the philosophers. Now, each philosophers for having the rice bowl has to take two fork of that spoon. Okay, so they have to take two fork of spoon. Then how do we execute? So we have written a piece of C code. So we have what we have done, we have taken a function philosopher. Inside that we are iterating this loop till all the philosophers in the you can say that dining arrangement is over. So how do I iterate? I have used a while loop. Okay. Now, if you look at this code, these two statements, these two statements will basically help the processors, or I can say the philosophers, to pick up the spoon which is available for them. So for, let's say, for the first philosopher, let's say P0, for the first philosopher P0, so what will be the value of I? So it will be 0, because for it will depend upon the number of, like on the processor's suffix. So here P suffix is what? 0, right? So I value will be 0. Next, when P will move to the next, I mean to say philosopher, so that time it will increment to 1. In that way, then 2. Okay, so for here, let's say for example, how we will be able to decide like which process will pick which fork. So it will execute these two statements. So once if it executes, how will it look like? So look here. Here I values how much? 0. Okay. So if I put here 0, take fork 0. So directly we can say that okay, it will be taking fork F0. Now After this, f0 p0 has taken. Then after this, which fork will it take? So how will I know? So I need not worry because I have another code. What is this code? Take fork. Which fork to take? I plus 1 modulo division n. So I is how much? 0. 0 plus 1 is how much? 1. 1 modulo n value is 5 because number of philosophers are 5. So 1 modulo division 5 is how much? 1. So it will take fork which one? Fork 1 because the value is 1 in that way. Okay. Then it will eat. Then once its eating is done, so it will put back those forks. So how will it put back? It will use the same logic. The first one is I, so it will use I. The second one is I plus 1 modulo n. So same thing, I plus 1 modulo n. So accordingly, we will get the same value, F0 and F1. So these forks have to be put back. Now, next P0's work is done. As we have said that we are taking this case to be that the philosophers are appearing one after another, not simultaneously. So next, after P0 is done, the next philosopher comes, P1. So here the value of I is incremented. So what will be the new value of I? 1. So again, what I have to do, I have to run the loop because the loop will be continued until and unless all the processes or the philosophers are available. So here modulo 5 is how much? 2. So this will be taking the second fork. So in this way, it will be completing the cycle in a serial way. That means when the processes are not appearing one by one. So here I have already listed that n is the total number of, you can say, forks which are available. Okay. Now, next is, let's say we have a situation where P0 is there and P1 also comes. Okay, then again, if P1 is there executing and then P2 comes, then in that situation, what will happen? Because both of them will be competing, then there will be basically the issue of basically race condition. Okay, we already have seen what is a race condition. So let us try to check like what will be the scenario in that case. So let us see we have a situation where P0 enters the dining, I mean to say arrangement, okay, initially. So once it enters, let's say P0 has just entered, it has executed, and it has executed the statement take for I. So what is I here in this case? So it's very simple. I is what? I will 0 because for first process P0, I value will be 0. Okay, and accordingly, when it executes this code, so when it executes this code, take fork I. So what is the value of I? 0. So it will take fork which one? F0. So hence we have F0. Okay, now before P0 could execute the second statement, this one. Before P0 could execute the second statement, then what has happened? Let's say uh, P1 enters. Okay, so before P0 could take the another fork, that is F1. So what will happen is P1 enters and shall execute this code. So P0 executed this code. P0 executed this code, correct? It was supposed to go here. Now, what has happened? Some interrupt took place and P1 came. So, P0 could not go to the second line of instruction. Okay, so P1 came. Now, when P1 came, again, it will execute all these lines of code and it will be entering into which line, let's say here. So it will be taking, it will say that take for, what will be the value of I here for P1 now? It will be 1. So it will be taking the fork F1. Okay, so P0 could take this fork F0. Okay, and before it could take F1, some interrupt took place and P1 came in that situation. And what happened? P1 executed this line, that is take fork 1, sorry, take fork I. And what is the value of I here? F1. So what has happened? P0 should have taken 2, but P0 took only one, that is F0, and before it could take F1, P1 came and it has taken whom? F1. Okay. So in that situation will continue. So what will happen, and hence P1 will pick F1. Now what will happen? However, P0 is waiting for F1 because he can eat the bowl rice with two forks. So P0 will have to wait now because he has no choice. Why? Because the fork F1 has been taken by P1. Okay, so F1 is already taken by P1. Okay, then what will happen? P1 will take F2 as well by executing the code. Okay, now P0 will get fork F1 only when P1 is done and release F1. Okay, so what has happened here is, let's say now P1, what will P1 do? What will P1 do? What will P1 do? P1 has taken fork F1 and P1 will be, let's say, for example, executing this code. So P1 will be executing this code as well. So if P1 executes this code, what will happen? P1 को F1 मिल गया. It has got F1. P1 will execute this code. So what will happen? Take fork I plus 1 modulo n. So what is I here? 1, because we are looking for this one. So 1 plus 1 is how much? 2. So 2 modulo 5 is how much? What is the remainder? 2 modulo division 5? It is 2. So P1, yes, P1 will be getting both fork F1 as well as F2. But what has happened for P0 for the first like process? It has to wait. So how long will it be waiting? It will be waiting for till that instant of time till P1 will not be sorry, yeah, P1 will not be releasing fork F1. So this condition is a kind of a hold and wait, isn't it? Someone is holding, that means P1 is holding the fork. Isn't it a hold and wait? P1, P naught required F0, F1. P0 got only F0, but P0 wants F1 also to eat the rice bowl. In between, what has happened? P1 came before P0 could take this fork. He took this fork and he took this fork also. Now, what will happen in case of P0? P0 now will wait for F1. How long will it wait? It will be waiting till P1 will not finish the use of F1, and until and unless P1 release, P0 can access F1 so that resources cannot be preempted. We can preempt all processes, but resources we cannot preempt. So what will happen? P1 will be holding and P0 will be waiting. So this is a condition of deadlock because we have a hold and wait condition. Okay, so such kind of issues are being basically tackled by the semaphores because we have come across a situation of race condition where one philosopher is waiting for a fork where that fork which the philosopher is waiting for, that fork has been taken by another philosopher. So what has happened here? That fork is available to some other philosopher. He's holding that fork, and the other philosopher who needs that fork, it is waiting. So we say that whenever such situation arises, that is hold and wait, it is a case of race condition. So how we are going to solve this race condition? We will be using the concept of binary semaphores. So is it clear the case? Okay, very good. So now let us see how we are going to deal with this kind of situation. Okay, so let us see how we are going to deal with this situation. So we have said that we can needing that is the first thing. So our forks and processes are five. So hence semaphore also we will be needing five forms. Okay. So how means so how we can arrange them? So So I've kept it. The subscript we have process P0. So semaphore S0. Process P1. Process P2. Semaphore S2. You can say uh, semaphores that we will be using from the array. Now we know that in binary semaphore, if you remember, the initial value of a binary semaphore is always equal to 1, isn't it? So what this 1 will basically say, this 1 will basically give me the idea that no process is using the critical section. Again, I'm saying one value in the semaphore will indicate that no process is being used in the critical section. So if suppose let's say semaphore value is 0, so what can like we know, what reference we can know, we can say that if suppose the semaphore value is 0, then it will indicate the other processes that one of the process is there in the critical section region. Okay, so that is the aim. Now there will be little bit of modification in the code. So what is the modification? Everything is same, but this part, this part, and this part, there will be little bit different because semaphores have come. Okay, so let us see what will be the difference. Everything is same. We will see that operations which are being performed by semaphore will be operations which are being performed by semaphore. Do you remember the operations which are being performed by semaphore? There were two operations, wait and signal, isn't it? Okay, and we have already seen like what is the purpose of having wait and signal operations. Okay, so let us try to analyze this situation again. So we saw that the main challenge was basically when we have a situation where you can say one process has taken the fork, but before that process could take the second fork, isn't it? Another process has come into the picture and have taken the fork away. So in this situation, the processes now one is holding the process who has taken it, and one has to wait till the resource is not available. That means the fork is not available. So that was a case of, you can say, a race condition, isn't it? So how do we eliminate that? So we have maintained a table here. Let's say, for example, process 0 is holding two semaphores, let's say S0 and S1. Process P1 is S1 and S2. Why two semaphores for one process? Because one process has two forks. So hence, two semaphores are being needed for one process. So P1 and P2, okay, again, two forks were there, F2 and F3. So hence semaphores also it is S2 and S3. So in that way this thing will be continued. Okay. So now let us try to say that now if P0 enters, okay, so we know that semaphore's value initially is what? All equal to 1, because initially if no process is being utilized in the critical section, then its initial value is 1. So all of them value will be equal to 1. However, it shall need two values, okay, for proper execution. That is for semaphore S0 and S1. Very correct, because P0 will be needing how many fork? Two fork, and each of the fork is having one semaphore, correct? So P0 will be needing how many semaphore? Two semaphore S0 and S1, okay? That is P0 has to change the
Sir,
values of two semaphores from, yes, tell me.
so the video is not loading. Can you please restart the stream? Like the video is like loading, but I cannot
Okay.
see anything.
Okay, okay. Is it fine now?
Yes, sir.
Okay. So now let us say, for example, we have a situation. Let's say P now if P0 enters, it shall need two values for proper execution, right? So which are the two values it will be needing for semaphore S0 and S1? So what does it mean? It means that P0, if it wants to use the fork F0 and F1, then it has to set the semaphore value of S0 and S1 from 1 to 0. That is the thing you have to remember. Again, I'm saying if P0 wants to use the two fork, which two fork? F0 and F1, then what it has to do? It has to set the semaphore value of S0 and S1 from 1 to 0. So the moment P0 will do this, what will it, what presently it will be telling the other processes that no, you wait, check the semaphore value. What is the semaphore value? S0 and S1 is 1, sorry, change to 0. So what will this indicate? It will indicate that the other processes will consult what is the semaphore value of S0 and S1. If I have to take for F0 and F1, okay, I have to change the semaphore value. If the semaphore values change, then it will send a notification to the other processes that no, you cannot take the fork. Okay, let's say P1 will request for S1 because P1 needs which one? S1. But if suppose P0 has set the value of S1 from 1 to 0, then what notification will be sent to P1? P1 will be notified if it tries to access S1 or let's say fork 1, then it will say that no, I cannot take. Why I can't take? Because fork F1 like given however which it wants to fork one which it wants to take, it will check the semaphore value, okay, corresponding semaphore value. So since the semaphore value is 0, so hence it will not be able to consume. Okay, so this will be a situation where P1 will be, you can say, blocked temporarily for consuming the you can say fork F1. Okay, why it will not be able to take? Because it has already been given to process P0. Okay, how did we do that? We have changed the value of the semaphore S1 is common to both P0 P1. So P0 has changed, has set the value, so automatically these two forks F0 and F1 are available to P0. So P1 when it tries to access those forks, so it will see S1 semaphore value of fork 1 is 0, so it will not be able to access. Till when it will not be able to access? Until and unless P0 has not finished the work. Now let us go to P2. P1 is
Sir,
blocked
sir,
temporarily.
can you
It
please
can't, so
repeat
it
that?
has to wait. Yes.
Sir, can you please repeat the table part again? Like the streaming was having some problems. Like from the table, like
Okay,
again.
okay, sure. See, from here, right?
Yes, sir. Yes, sir.
Okay. So, okay. So what happens is we have maintained a table. Okay. Let's say, for example, for every situation, let's say P0 needs two forks, F0 and F1. So for every fork, what we have done, we have connected a semaphore. Okay. So let's say if suppose a fork is available, let's say fork F0 is available, let's say here fork, if suppose fork F0 is available, so the corresponding semaphore value of this one, if suppose this is available S0, semaphore value for F0, let's say S0, the corresponding semaphore value for this one will be equal to 1 if F0 is available. The moment F0 is assigned to P0, okay, the moment P0 takes this spoon, this fork, so the semaphore value for this fork will be set to 0. From 1, it will change to 0. So what will this message indicate? It will indicate that this particular process now no, it is being given to some other process. Similarly, here also, if suppose P0 wants to consume this rice bowl through this F1, through this fork. So what will it P0 do? P0 has to change the value of the semaphore associated with F1. What is the semaphore associated with F1? S1. So that semaphore of S1, P0 has to change from 1 to 0. So the what will it do? It will send the notification, not notification, but you can say that when other processes will try to access the fork, it has to check first the associated semaphore value related to F1. So what is the associated semaphore value related to F1? S1. So it will check S1 का value क्या है. So it will see that oh S1 का value तो zero है, तो मैं ये fork नहीं ले सकता हूँ. So this will be blocked. So P1 will not be able to take the fork. So this portion of the philosopher, it will not be able to execute. Okay, why it could not? Because already P0 has set the value of semaphore of F0 and F1 from 1 to 0. So same thing we are saying. It has set. So once it has set, it will not be able to use the fork. Now P1 has to wait because S1 is not available. That means fork 1 is not available. Now we will go to P2. P1 is not it has to wait, so it will be like that only. Okay. Now we'll go to P2. Now when we will go to P2 here, we will check here. So we will check the semaphore value of fork F2. So what is the semaphore value of fork F2? What is the semaphore value of fork F2? For P2, what is the semaphore value of F2? Fork F2 is available because no one has taken only S1. There was a problem, right? S2 could not be given to P1 because the before only due to this S1 problem, P1 is in the blocked state. Okay, so S2 is available. Okay, and what about S3? That means fork 3 is fork 3. We will check here in the diagram again. Is fork 3 available? Yes. P2 will check for F2. P2 will check for F3. So both the forks are available. So that means the semaphore associated with F2, that is S2, and the semaphore associated with F3, that is S3, its value will be changed from 1 to 0. So the moment we do this, what are we trying to say? We are trying to say that fork F2 and F3 has been given to some process, and those forks will not be available to any other process in the dining table. So next time if P3 wants to access F3, will he be able to access? No, he will not be able to access. Why? Because the semaphore value associated with F3 is how much? Zero. So the moment zero, P3 sees zero, semaphore value of F3, it will understand that this fork is not available. P3 also will be in the block state. Okay, so this part also will be in the block state. So till when they will be in the block state? They will be in the block state. Okay, P1 will, like for example, P1 will be in the block state till when? Till P0 does not finish the fork utilization. He does not finish the rice bowl, and he does not finish putting the fork back. So same concept only. It will take the fork, so it will be sending weight. We have to perform the weight operation. The weight notification has to be generated, and once it puts back the fork, then it has to be signal. That means it has to be signaled to other processes that the forks are available. So once the forks are put back, the semaphore value also again it will be zero. So that when other processes will check, okay, that semaphore like that fork is available or not. So from that semaphore value, yes,
Sir,
tell me.
sir, sir, P0 will need F0 as fork, right? P0.
Yes. P0, like to access F0, to access, like to get the fork F0 for P0, if the fork value here, okay, the semaphore value here has to be changed from 1 to 0.
0.
Okay, semaphore value, the moment semaphore value is 0, that means that fork F0 is given to P0. Because for every fork, okay, once semaphore is attached. Okay, similarly for this also, if suppose I have one P0, if I have to change the semaphore value of that fork F1 fork, so what is the semaphore associated with that fork? S1. So I have to change this one to S1. So what is the semaphore associated with that fork? S1. So I have to change this one to S1. 0. So
Zero.
the moment this is changed to 0, that means both the forks F0 and F1 are being taken by who? P0. Is it clear?
Yes, yes.
Next time, when suppose P1, okay, when suppose P1 will try to, let's say, get fork F1. So which semaphore it will need? S1. So it will see S1, but S1 we have already given, already its value set to 0. That means fork is given to P0. So S1, due because of S1 being 0, this the process will not be able to execute. So same thing, if this is not being able to execute, it will check the other process which is available. So now we have that we need how many forks? Two forks, F2 and F3. Then the what you can say, the semaphore value for fork F2, the semaphore associated with fork F2 is S2. So if fork F2 should be given to P2, its semaphore value has to be changed from 1 to 0. Similarly, it needs fork F3. So for fork F3, we have semaphore S3 being attached. So its value has to be changed from 1 to 0. So the moment we do this, then fork F2 and F3 are available for P. Okay, then P3 will not be able to execute. Why? Because S3 is common. So S3 we have already given, so we will not be able to. Okay, so what will happen in this case?
So, sir, the semaphore value is a binary right now, right? Like 0 and 1.
Processes. Like here, P0 and P1 are cooperating processes. Why? Because they are sharing the common fork F1, right? So when P0 enters in the critical section, P1 will not be able to enter. Why? Because they are cooperating processes. This is basically your very short. From here, basically, we will see that which process has. Sorry, I can't get you.
No, sir, I wanted to ask if the semaphore value
Ah,
was binary, like 0 and 1, right?
yes, yes.
Okay, okay. Okay, sir.
I can you repeat one more time the question?
Sir, I said the semaphore value was binary, right? Like 0 and 1.
Yes, yes. Zero
So
and
if
one
the
only.
value is 0, then the fork is available for like eating, right?
No, no. If the semaphore value is one, then the fork is available for eating. That means
Yes,
other
sir.
processes can take. Okay,
Okay, okay.
but if it's zero, it's not.
Okay, sir.
Okay. So when coming to the code, okay. So for coming into critical section, the entry code, that means take fork. There is a part, no, take fork. Okay, so this part is the entry code. So the moment this is executed, then that like I mean to say process P0 will be able to enter into the critical section, eat the rice bowl, and then after that it will be able to exit from the critical section. Okay, so basically you can say this is the entry code of the critical section. So inside critical section it will execute. What it will execute? It will do the eating of the rice bowl. Once it is done, then it will be exiting. Okay, so this is the exit code. So this is only for your understanding. Okay, I am writing here. Okay, so once it has done the eating the work, so it will put back. So how will it put? I've used some function, same type of function. The only difference in the code in the previous one is that here we are using the wait function. Okay, that means if one is consuming, the others have to wait, and then once it is done it will signal out that okay, forks are available, the other process can take it. Okay. So one more like question may be asked. Okay, one more question may be asked. This is very important. Like for example, we know that P0 and P1 are cooperating processes. Why? Because they are sharing a common section, common element, that is F1. F1 is the common element which is being shared between P0 and P1. So for such kind of situations or processes, only one process can execute in the critical section, isn't it? Like if P1 has to wait, if P1 is executing, P0 has to wait. Now let's say, for example, we have a situation, like for example, P0 has entered in the critical section, then can P2 also enter into the critical section? Can that be possible? I'm saying if P0 is has entered the critical section, can P2 and P4 also enter the critical section? Is it possible? P0 and P1 can't enter together. Why? Because they are cooperating processes. There is a dependency. The execution of one process affects the result of the other process. So there is some kind of dependency. But I am saying that if suppose we have a situation, let's say P0 has entered into the critical section, and I am saying, can P2 also enter into the critical section in the same period of time? Is it possible? Tell me. Is that possible? What do you think? You can be wrong, but you can try. Okay, Abhilasha, tell me why they can execute, or like why both can enter into the critical section.
So because they are not using the same semaphore.
Okay, not same semaphore. You're partially right, because they are not using a common element there. Like P0 and P1, the element which was common was the fork F1. No, it was in between them.
Yes.
but but in case of P0 and P2, see, if you see the diagram also, in case of P0 and P2, let's say between them, what are the forks that P0 need? F1 and F0. P2 needs F2 and F3. So there is no, so they are not cooperating process, they are independent processes. So in case of independent processes where there is nothing common, there is nothing shared, there is no problem even if 10 independent processes can enter into the critical section. But if the processes are cooperating processes, okay, then only one process only can enter into the critical section. So that has to be very clear. Like processes, if they are cooperating, then they will, only one process will be able to enter into the critical section and execute, if it is a cooperating. Why? Because there is a shared thing which is there. But in case of independence, since the result is not affecting one with the other, so they are running parallelly, with there is no common intersection, there is not a problem. So those kind of like short tricky questions also might be asked. Okay, so those things you
Okay,
have
sir.
to know. Okay.
Okay, sir.
So, yeah, so any query so far? Case 2, then we will go for case 3. Others type in the section if you have problem. Yes, the forks are five different resources here. Okay, the forks are five different resources. To whom they are the resources? To the process. Okay, and semaphore basically are a kind of way to know like whether those forks are available or not. So semaphores are basically only values which basically tells the processes that whether those forks are available or not. So depending upon the number of forks, that many number of semaphores will be there. That is the logic that they have used. One, it is always one. That means if semaphore value is one, that you can say that the resources are available. Okay, or the forks are available. And if it is set to 0, then the forks or the resources which are there are not available. Okay. Now, who sets these values from 1 to 0? Who do you think will set the value from 1 to 0? Who will change the semaphore value? Who do you think? You can make a guess. Who will change the semaphore values? Any idea? It is the processes only. Okay, so the process, once it's take, it executes the code. So automatically the value of the semaphore will be set. Okay. Okay, so next is, let's say we have another situation. Okay, let's say we have another situation. Like in first case, we have seen that there was a series of you can say execution of processes in a serial order. That means there was no dependency. In the second case, what we have seen is we have a problem with the race condition. There was a problem, like for example, if P0 is there, P1 came all of a sudden and then it executed, then it snatched away the fork, then P0 had to wait. Then we saw that how we tackled with the semaphore, isn't it, using semaphore. Now let's say we have another kind of situation. So let us say that P0 will come first, it will execute this part of the code, take fork SI, and using this one. Okay, same code only I'm saying. So it will be executing the first part of the code. This is case 3, let's say. Okay, so it will execute another part of the code. So let's say this part of the code, the first process executed. So what did it do? It has taken the resource fork F0 and has set the semaphore value from 1 to 0. Okay, so that means others will be like knowing, okay, this fork is now no longer available. It is being taken by some process. Now the moment it could go to the another like co-statement, okay, some preemption took place. Okay, preemption took place. So this preemption can be for many reasons. Let's say some interrupt took place, or maybe let's say for example some higher priority process came, so P0 had to be stopped, and then P1 control to P1 the control had to be given. So what will happen? So let's say it executed the first statement, it got the fork 0, P0. Now after this, P0 is preempted, P0 had to be pulled out. Okay, and P1 enters into the scene. So P1 now will change the value of that fork. That means it wants to take the fork, so it will change the value of the semaphore associated with that fork from S1, of S1 from 0 to from 1 to 0. Okay, again I'm saying P1 will try to take the fork F1. So in order to do that, it will change the semaphore associated with that fork. Okay, its value, it will change from 1 to 0. Okay, so the moment it does, what will happen? It will take fork F1. Okay, so it will take fork F1. So the it executes this one. So P1 also executed. There was a preemption. P1 came. P1 also executed this. Okay, so it got this fork. It could, before it could go this one. Again, there was a preemption. Okay, then what happened? Another process came, P2. So P2 also executed. Again, there was a preemption. It could execute only this code. So in this way, that means what is happening after every, you can say, execution of this code, for every process, there is a preemption. Okay, the preemption can be various reason. Okay, like maybe some interrupt took place, or maybe a higher priority process came. Many reasons can be there. Okay, so as a result, what is happening? As a result, what is happening? If you look here, P0 has only one fork, P1 has only one fork, P0 has fork F0, P1 has fork F1, P2 has fork F3, P2 has, sorry, has fork F2, P3 has fork F3, and P4 has fork F4. Now, what has happened? This has become a state of deadlock, because for eating a rice bowl, every philosopher needs two forks. But here, every philosopher is, you can say, devoid of one fork. Okay, it is lacking one fork. So this is a kind of, again, there of a deadlock. Okay, so we will see here same thing. So whenever P2 does the same, it changes the value of S2. There is a preemption. P3 enters. P3 also does the same. It takes fork F3. Whenever it wants to take the next fork, another process comes. There is a preemption. So in this way, what has happened? All the semaphore values are changed to zero. That means none of the forks are available. So what will happen now? All the processes will be in case number two, at least two independent processes could do their work, or the processes which were independent. Here, what has happened, even if the processes are independent, but because of the condition every time, but because of the continuous preemption, okay, every time there is a preemption, every time all the processes now are blocked. So this kind of situation which gives rise to circular wait, all are waiting in a circular wait, isn't it? It's a circular pattern. P0 is waiting, P1 is waiting, P2 is waiting, P3 is waiting, P4 is waiting. It's a kind of a circular structure. All of them are waiting. Why? Because all the semaphore values now are changed to zero. The moment semaphore values are changed to zero, what message it is passing? It is saying that no resources are available. So this situation is basically a case of deadlock. Okay. So the same table only we have made. So such kind of situation also arises. Okay. So these are the three cases which basically we say as dining philosophers problem. Okay. So how we will change also we will see. But are these three cases clear? Are these three cases clear? The problem I mean to say. Okay. So you want me to do the solutions of this one today and bounded buffer problem today, or you want it tomorrow?
Tomorrow, sir.
Okay, because not
So tomorrow is better
yeah,
because
uh,
lots of students are not.
not there, no.
Yeah.
Okay. So did you all understood or not today the this one? What is it called? Dining philosopher. The issues, the three problems at least.
Yes, sir.
Yes.
Sir, can you repeat the last case?
Okay. Mehboob is typing something. Okay, last part. The thing is, what has happened is in this kind of situation is like, for example, P0 has taken fork F0. Okay, so it has executed this code, the first code. So the moment we execute this code, this fork has been taken. Now, before it could go to the next line of code, some preemption took place. That means some interrupt took place, the control came out, and some other process came. So the moment other process came, again this line got executed, this line. So the moment this line gets executed, what has happened? P1 will get this fork. So before P1 could take the other fork, that means before that process could execute this line of code, again some preemption took place. Okay, that means some other process came. So P1 control now will be out and P2 will be given the control. Again, when P2 entered and executed this part of the code, it got the fork which is available, but it needs this also. So before it could pick this like fork, okay, before it could execute this code, because this code means the next fork which we can pick. So before it could execute this code, again some preemption. Okay, then P3 was given the control. So in this way, all the processes have taken only one fork. So the moment they have done this, what they have done, that means all the semaphores also which are there related to every fork, those semaphore value also has been changed from 1 to 0. Why? Because all the forks are now like given to someone, at least one also, but all of them are occupied. So what will happen now? Neither of the processes can eat the rice bowl, none of the philosophers can eat. So all of them will be waiting. So what will happen now? This will be a pattern of circular wait. Okay, so this kind of situation where all the processes are waiting, okay, for the resource to be available, this kind of situation creates a deadlock. Okay, so these are the three situations that we basically face for you can say dining philosophers problem. Oh, Yes, it is better to mention, okay, for clarity. I did not mention, but it is better. Like here, no, like whatever is happening. Like for example, P0 was changed to zero once. Sorry, S0 was changed for F0 was given to P0. So this was still one. Preemption took place. So after preemption took place, it could take only this fork. So this can be changed to zero, but this one was preempted. So that way you can put according to your choice. Okay.
Okay, sir.
Okay. So I think that will be fine. Okay, and we will look into tomorrow's class. Okay.